It's not every college professor that will invite students to their home to light trees on fire, but that's what you're listening to. It's research, I promise. Important research for those of us in the Pacific Northwest and elsewhere who are very interested in understanding the path of a wildfire. Wildfires are common around the world in places where summer heat, drought, and frequent thunderstorms create ripe conditions. But as global temperatures rise, that means hotter, drier summers, and the number, duration, and intensity of wildfires is also expected to increase. Already, here in the Pacific Northwest, the past few years have seen record-breaking fire seasons, both in terms of the area burned and the dollars spent fighting them. The story is similar in places like Australia, Southern Europe, and parts of Russia. As part of the effort to adapt to this new reality, researchers here at Oregon State University are working to understand how to control or prevent wildfires. But to do so, you have to learn how they spread in the first place. For one researcher, who we'll talk to today, that means, somewhat ironically, burning a lot of trees. From the College of Engineering at Oregon State University, this is Engineering Out Loud. I'm Owen Perry. David Blunck is an associate professor of mechanical engineering here at Oregon State. His primary area of focus is combustion and propulsion. Earlier in his career, this meant researching turbine engines for the Air Force. But after coming to OSU, he started to focus on new areas.
And I remember I sit in my office one day and I was just taking stock of Oregon and Oregon State, and I recognized that the College of Forestry is excellent. And I also recognize that in the Western United States in particular, that wildfires can be quite detrimental. And I also thought that it would become even more and more pressing. And so I thought, well, I'm going to start studying wildfire.
It just so happened that around that time he saw a grant solicitation that was specifically interested in the mechanics of firebrands.
A major way that fires can spread is through firebrands, which are bits of pieces of burning material that break off. And they can go through the air. They can be transported miles in some cases. And when they land, if they're hot enough, they can start new fires.
A few summers ago, the Eagle Creek fire burned 50,000 acres along the Columbia River, which is one of the largest rivers in North America and makes up the Oregon-Washington border. The fire actually jumped the river, sparking a smaller fire on the Washington side.
And so after the fire, we went in and estimated the distance that it took for this fire to jump. And we estimated it was 4 miles. So presumably a firebrand broke off on the Oregon side during the Eagle Creek fire and then was lofted by the winds across the river, landed somewhere where there was receptive fuel, and started a new fire. And that certainly is not the farthest that firebrands have been reported to travel. I wouldn't say it's probably typical to go miles, but it's certainly not unheard of.
Given their role in spreading wildfires, there's a lot that's not known about how firebrands form and how they travel, or what factors affect the number of embers that come off of a particular type of tree. Knowing this kind of information could lead to better fire prediction models and help communities better plan for wildfires.
My extent of firebrand knowledge was watching embers break off at campfires. Like I'd never thought about it before, so I didn't know what research to do or what the needs were. And so I read a lot of papers from journals to try to understand what people have studied and have not studied about wildfires, and had a lot of conversations with my collaborator, Dr. Brett Butler, and collectively came up with a research idea, which is to better understand what controls the formation of firebrands. And that led to our first proposal, and that led to an ongoing collaboration. And at this point, I have had or am currently working on my 5th research project related to wildfire.
Let's walk through some of those projects so that you can get a sense of the breadth and scope of what he and his team are studying.
So the very first project was looking at firebrand formation and trying to understand what controls the release of firebrands. So things like the size of the twig, for example, or the species.
Another project is looking at how duff, or the decaying plant matter that covers the ground under trees, smolders and can eventually restart fires.
I have another project looking at the burning of live fuels. So you have trees that maybe are dried out, but they're still living. They're still lush and they're still green, and they also burn. And most of the models and what the community has studied up to now have been dead fuels, or just assume that a live fuel is something that is dead but has lots of water in it.
A fourth project looks at what happens when a firebrand lands on a fuel bed and the factors that influence whether it ignites the fuel or not.
And then the final project, which we're working on, is continuing to look at firebrand formation. And specifically, we're trying to identify how many firebrands are released per pound of fuel that we burn.
I think I should pause for a moment here and reassure you that most of this work is not being done in active wildfires. And when David says we burn, he's talking about doing so in very controlled environments. The research does involve burning trees, but in a safe way.
We have a large gravel area, and we go out to the Oregon State Research Forest, and we go out and we harvest Douglas fir, ponderosa pine trees, and they are about 12 to 14 feet tall. Last year we were burning some 20-foot tall trees. So we then take them in our gravel area and we stand them up vertical like you would a Christmas tree, and then we put straw underneath those trees, and then we'll light the straw at one end, and then the flame then creeps along the straw and it gets bigger until eventually those flames will interact with the tree and then cause the tree's portion or all of them to burn, and they create big flames. And then as these trees are burning, there'll be bits of burning material that break off and then get lofted up just in the air, and then they'll come down and land in this area where we have the gravel.
Spread out on the ground around the tree are sheets of fire-resistant fabric. When the firebrands or embers float back down to earth, they land on the sheets and burn up, leaving scorch marks of various sizes. You can see a photo of what this looks like in the show notes.
Then we take the sheets, we take it back to our lab, we set up cameras and lighting, and we take pictures of the fabric, and then we take those pictures and then use computer software to back out the number and size of those char marks or the burned spots on the fabric. And then we use that to back out a total number of hot embers or firebrands that came down on our sheets of fabric.
The group has done this for a number of species of trees and shrubs that grow in the Pacific Northwest.
So far, we've determined the total number of firebrands and normalized it or divided it by the amount of fuel that's consumed. We've done that for sagebrush, ponderosa pine, and Douglas fir.
They found that pound for pound, sagebrush produces the most firebrands of all the species studied. But you have to remember that sagebrush are much smaller than massive Douglas firs, which provide a lot more fuel for fires. Still, there are some interesting findings about bigger trees.
Our results suggest that either the total number of firebrands per amount of fuel consumed stays the same or decreases as we increase the height of the tree. And I wasn't expecting that. And we're still wrapping our mind around why that may be, but that was an unexpected result for us.
Now David and his team are expanding their scope beyond the Pacific Northwest to species in California.
In Western Oregon, where we live, we may look out and see a Douglas fir forest. Out there, they would see something called chaparral, which is like an ecosystem down there. And then within chaparral, chamise is one of the major species. Fires can spread through chamise, they can generate firebrands. And so that's what we're currently studying this spring.
They're also looking at how the moisture content of a tree affects firebrand generation.
So we have some trees that were harvested 2 days ago. So these are live trees, so the moisture content should be very high. I mean, it's as high as it's ever going to be for those trees, at least for this time of year. And then we have trees that have sat out for over a month now. They're no longer green, they're orange. And so we're really doing two extremes.
By comparing trees with different degrees of moisture left in them, they'll get a sense of the role that moisture plays in the generation of firebrands.
And it may be very little, it may be a big extreme, but at least we're trying to bookend our results to better understand the role of moisture content and influence on our results.
Ultimately, the data collected can be used in models to predict where and how fast fires will spread, depending on the types of trees that are burning.
This technique that we have developed to really estimate a total number of firebrands, no one's done that before. And so I think collectively for the firebrand and wildfire community, is starting to apply this technique. And hopefully they can improve on it, but I think it's a great foundation. I like to think it's going to take a next step forward in how we view and do firebrand research.
Of course, during wildfires, it's not just trees that burn. It's also homes and other buildings. Last year, fires decimated towns in Oregon like Detroit, Blue River, Vida, Phoenix, and Talent. This year, the Caldor fire in Northern California has destroyed hundreds of structures as it's ripped through small towns.
So once the flames transition from a forest into like houses, like a house like we're in right now, at some point the source of firebrands may not be the forest, or they may be the firebrands from the forest may be secondary, and it may be the firebrands that come from burning homes or burning structures. We really don't have a good understanding about firebrand production numbers or generation rates from structures, and so I want to extend into that. I think that's could be very impactful, and it's a needed area of research.
In the future, David wants to expand his research to look at how burning buildings may produce firebrands.
So, Owen, when I first started this research, I started because I saw a research need and an opportunity, and I still do. But as I've become more aware of firebrands, I've also become more engaged in education. So how do we as homeowners, how do we help protect ourselves from firebrands and from flames? And in particular, the burns that happened in Western Oregon this last fall really brought it home to me how important it is that we as homeowners educate ourselves about the risk of firebrands.
Immersing himself in wildfire research and thinking about how homes and buildings burn has really gotten David thinking about how to help limit that damage.
To put in perspective, my parents live in Canby, Oregon, and they went to a level 2 evacuation order. And so, of course, as a son who studies wildfire and I want to be a good son, I felt like I should go help. So I drove up there to Canby, Oregon, kind of opposite direction of all the other way the traffic was going. And I went up there, and my parents have about 3 acres, and they are trying to recreate the Garden of Eden. Like, it's lush and it's green, and they've been watering the entire week because they were expecting this wall of flame. If the fire was going to come to Canby, this wall of flames, and it could get past their green grass. That's certainly valid. But having studied firebrands, I actually went up on the roof, and I took a leaf blower and I blew it out the roof, and I walked around outside, and I looked at a few spots that were dry, and I got them wet because I just realized that their mode of protecting their home was valid for a wall of flames, but wouldn't necessarily be sufficient for firebrands that could come down up in their house and their gutters. They had some leaves in their gutters, so firebrand could come down and land. And then I went around and visited some of the neighbors and did the same type of thing. I went very much with a filter of, if a firebrand came down, how could it potentially start a new fire? And I just realized that my parents and neighbors, very competent, very smart, but they hadn't thought about the risk of firebrands. In general, as a public, we tend to be naive just about the risk of firebrands, and there's a lot of simple steps we can do to help reduce the risk of firebrands. I think if we just do an audit of our home and walk around and say, if something hot or a flame were to land in this spot, or several things that were hot were to land in this spot, could I start a new fire?
We recorded this interview as the summer of 2021 was just kicking off. But for both David and I, the memories of 2020's horrific fire season were still fresh. More than 1 million acres burned in Oregon alone. And places that were spared the flames were still blanketed with thick smoke that made it hazardous to breathe the air outside for over a week.
And I think this last summer, unfortunately, was a wake-up call to a lot of us in the western part of Oregon that they can happen close to home. And it's on all of us just to take simple steps to be prepared.
The goal of David's research is to provide data to other scientists who are modeling fire behavior in real time. If they can better understand how a fire might spread, firefighters may be able to marshal their resources to where it's likely to go, and give those in its path more time to prepare. Thanks for listening. We'll be back with more episodes about engineering for natural disasters, including more research dealing with wildfires soon. This episode was produced by me, Owen Perry, with sound editing and production assistance by Will Havner and Rachel Robertson. Our intro music is The Ether Bunny by Eyes Closed Audio, which you can find on SoundCloud, and it was used with permission of a Creative Commons Attribution license. Other music and effects in this episode were also used with appropriate licenses. For more information, visit engineeringoutloud.oregonstate.edu.
I have a funny story about when we started this research. With that?
Yeah, sure. I like funny stuff.
Okay, so I'm going to give you full disclosure on this, Owen, and I may regret this, perhaps. So, so the very first time we wanted to do one of these burns. So again, we have a Christmas tree stood up, straw underneath. We realized we're generating firebrands, and firebrands spread fire, and so that could be worrisome, right? And so the very first time we're going to burn, we had someone from the fire department. They want to come out and observe it. I had water going from a pump down by the river, and so I could probably move about 70 gallons of water per minute. I mean, I was ready. I had the sprinklers going. We had safety protocol in place. If there's a fire that got a hand, this is what we do. We'd shift the water line around. I had a garden hose. So we were, what I thought was very prepared. So we lit the straw progressed, it hit the tree, and the tree didn't burn. And so then I took lighter fluid and I started dousing this tree. It still didn't burn. So finally, I guess my head was down and tail between my legs. The gentleman from the fire department, very kind, very nice, as he's leaving, he said, "I don't think you need to ask us to come back again. I think you're okay." And so fortunately, we've had a lot greater success since then at burning our tree zone, but that was a very humbling experience as a wildfire researcher to not even be able to burn a tree.